Eğer ki hayatımızda hiç eğer olmasaydı nasıl olurdu? Size şöyle söyleyeyim. Her şey daha az parlak, daha az yeşil olurdu ve daha az parlak yeşil. Çünkü eğerler ormanların derinliklerinde tek bir kibritle derinlerin kıvılcımını ateşler. Eğerler Nobel ve Guggenheim'ın aklına takılır ve o kodu bu kodu çözerler. Eğerlerle içinizden haykırmak gelir. Eğerler bariyerleri kırarlar. Asla yalnız yürümezler ve aşırı bulaşıcıdırlar. Eğerler aşikardır ve son anda golü atarlar. Eğerler dünü umursamazlar, robotlarla bile konuşabilirler. Karşı takım soluklanırken oynamaya durmadan devam ederler. Sadece basit bir kelime öyle mi? Hayır. Eğerler asla uyumazlar, hep daha fazla çaba gösterirler. Eğerler bakar, araştırır ve en beklenmedik zamanda ortaya çıkarlar. Eğerler klonlanarak çoğalırlar. Acaba gerçekten yapabilir misin? Yaptın bile. Eğerler aklınıza girmeye çalışan güler yüzlü şakacılardır. Eğerler kapıları açarlar, asla kaybetmeyeceklerini bilirler. Ve biraz gün ışığına her zaman hazırdırlar. Her şey bir eğerle başlar. Çünkü eğerler ne zaman dönüşür, ne zamanlarsa şimdi. Ve şimdi nasıla dönüşür. Nasılsa asıla. Eğerler bakış açınızı değiştirir. Eğerler oyunu değiştirir. Eğerler dünyayı değiştirir. Biliyoruz. Çünkü biz eğerlerle çalışıyoruz. Yakın Doğu Üniversitesi.
Dear colleagues and participants, it's a great pleasure for me to welcome you all to the second for the Additive Manufacturing Regenerative Medicine Symposium 2022, organized by Nearest University Center of Excellence, Tissue Engineering and Biomaterials Research Center. I would like to thank our partners, Sabancı University, Sunum Nanotechnology Research and Application Center, Nearest University, Narita, Nearest University, Dasam Institute for their valuable supports. For the Additive Manufacturing Regenerative Medicine Symposium aims to bring together researchers, scientists, and scholars to exchange ideas, present sophisticated research works, discuss hot topics in the field, and share their experiences on all aspects of biomedical engineering and systems. The second 4D Additive Manufacturing Regenerative Medicine Symposium will be one day that means gathering the key players of the biomedical engineering and systems community and related sectors. Symposium presents the latest technologies and developments in smart materials, additive manufacturing, and intelligent designs, alongside the current issues of concern in the future development of 3D, 4D printed devices. This symposium will provide a forum for scientists working in the fields of smart materials, advanced modeling, and 3D, 4D printing technologies to discuss and present their work. Aims of this symposium is to bring together the most recent research on a variety of existing topics such as, but not limited to, new material design and functionalities, metamaterials, smart materials, dynamic materials, lattices, advanced additive manufacturing techniques of smart materials, 4D printing, bioprinting, multi-material printing, additive manufacturing process, hybrid additive manufacturing, design methods for smart materials and additive manufacturing using artificial intelligence, advanced modeling and simulation, current issues of concern in the further development of 4D materials design and additive manufacturing. On this note, I would like to thank the organizing committee for putting this event together. Let me also thank all of you for your participation. I wish everyone a fruitful and enjoyable scientific symposium. Thank you. Now, For the first presentation, it's a great honor for me to invite distinguished research professor Ali Koshar from Sabancı University. He earned his master's and doctoral degrees in mechanical engineering from Rensselaer Polytechnic Institute. He is focusing on the design and development of new generation micro heat sinks with functional surfaces and microfluidic devices, including cavitation on chip devices. His research interests constitute a spectrum covering heat and fluid flow in micro and nanoscale, consideration, boiling heat transfer, microfluidic systems, and cavitation. He co-authored over 150 research articles in top journals and 80 conference papers in prestigious international conferences. He has also a co-inventor on 7 granted patents and 7 pending patent applications. He received numerous national and international honors, including the Prominent Researcher Award, Micro FIP Prominent Researcher Award in the 2021 Microflow and Interfacial Phenomena Conference, Middle East Technical University Prof. Mustafa and Parlar Foundation Science Award in 2021. He is currently leading a large research group consisting of members from various disciplines, graduate students, and engineers, and to bridge different disciplines such as energy, nanotechnology, applied physics, bioengineering, biochemistry, mechanical engineering. He has been successful to secure funding for his research activities from a wide variety of national and international resources. He also serves as a reviewer in many prestigious journals and is a subject editor in the Applied Thermal Engineering Journal. He is the co-director of Center of Excellence for Functional Surfaces and Interfaces for Nanodiagnostic, EFSUN, and a distinguished researcher of Sabancı University Nanotechnology and Application Center. He was recently elected as a member of Turkish Academy of Science. Now, Prof. Dr. Ali Koshar is going to present metal printed small scale hydrodynamic cavitation probe for biomedical applications. Prof. Dr. Ali Koshar.
Thank you very much for the introduction. Let me right now start this. Okay. Here. Okay. Thank you. Also, thank you for the organization of this nice event. Today, I will talk about biomedical applications of hydrodynamic cavitation as an alternative approach. You can see cavitation in fluidic devices, particularly turbomachinery, and you can consider it as a kind of opposite of boiling. In boiling, what do we have? We have a fluid, and we heat the fluid up so that we have phase change from fluid and liquid to vapor. In cavitation, instead of increasing the temperature, we reduce the pressure, local pressure. And with the same effect, we have a transition from liquid to vapor. And in turbo machinery, you can see in the fans or pumps, there are local, low local pressure zones where this phase change takes place. For example, on a propeller, where we have a gas bubble, and when the pressure increases, then what happens? A gas bubble collapses, and when it collapses, we have shock waves and high velocity liquid jets on the surface, and as a result, we have catastrophic damage, noise, and also decrease in the efficiency. In turbo machinery, it's something which should be avoided. But if we decrease the size of the systems, we could maybe use it for good means. This is the motivation behind our study. How can we do this? Of course, one can do it with an acoustic field, for example, ultrasonics. But here we have a hydrodynamic means to have it. Suppose that we have a flow inside a channel. All of a sudden, we restrict the flow using a small orifice. We have then a sudden reduction in the pressure. So we create low pressure at this region. And as a result of this, if the low pressure reaches a certain critical value, we start to have the phase change. So this is how we can generate cavitation bubbles in a fluidic system. And you can do it, of course, in a small scale. And if we do it in small scale, there are certain differences compared to large scale. First of all, the bubbles emerge from kind of cavities or roughness elements from the surface. And as a result, they also, of course, if we have cavitation, it's also extremely difficult to just extinguish it, eradicate once it develops. And we can, due to the small scale of our system, we could have flow choking. What I mean with flow choking is that we cannot increase the flow rate beyond a certain value. And we have nucleation from the surface. So surface nucleation is more dominant in small scale. So surface topology will be important. So after this introduction, maybe I can start to mention about the kind of cavitation probe which we designed and developed. Here you can see it. And this cavitation probe is designed in such a way that it fits to a kind of conventional endoscopic probe. And this, of course, will be then compatible with many systems and also with in vivo experiments. The concept is rather simple. This is the concept of this. So we have the flow, right? We generate a flow using a high pressure source, and we propel the fluid. Then we pass it through flow restriction, and we generate cavitating flow. And then using a manipulator, we can target it to the desired location where we would have, of course, biomedical treatments. Here you can see the subsystems of our device. We have, of course, a fluidic system with relevant elements, filter, valves, gauges, and of course the probe. And we have cystoscopy system so that we can fit our probe to this system. Then using a joystick, both automatic and manual way, we can actuate the system, and we can then target it to the desired location. And using a micro camera, we can also see what we are doing. So here we have 4 different sub systems. And this system, of course, is designed in such a way that it could also allow in vivo experiments. And if we zoom in on a cystoscopy probe, it's designed as flexible pieces. You can see, and each piece is connected to each other. We have one hole for the probe, another for the camera, and 4 tendons so that we can manipulate this in 3 dimensions. so that we can really fine target our cavitation bubbles. And of course, it's very flexible, I should say. It can bend, and it can also allow rotation as well. These features serve for fine targeting. And for fabricating the probe, we exploited additive manufacturing. And we used three techniques: one stereolithography, the other selective laser sintering, and for the final version, direct metal laser sintering, where we have the metallic probe, and we use this metallic probe in vivo experiments. So we exploited three techniques. So for stereolithography, we could have a resin material version where we could at least make preliminary tests and have an idea about how the system will function. And then we used Sls 3D printing, where we will have a nylon probe, and we use this nylon probe for in vitro tests, and we could also integrate our actuator to this system, and we could both manually and automatically control this and find target using this probe. And for final ones, we used aluminum alloy, and we use this version in vivo tests, and it's more durable. At the same time, it's also rather light. So we used a metal printer located at Fatih Sultan Mehmet University, and we could fabricate the parts, needed parts, which were defectless and which were also suitable for in vivo tests. And you can here see the kind of fabricated versions, metallic versions of our probe. And at the same time, of course, we made sure that it is user-friendly, and we can, for example, an expert could use and manipulate this using a joystick, as you can see. And in this unit, of course, control unit, we have standard components so that we can actuate the related parts. And using for steel tendon lines, we can steer the probe, and we can target it to the desired location. Here you can see the tip of the probe. It's metallic, but we also integrate an orifice made of PEEK tube, and it's rather short, few millimeters, and it is inner diameter is around 250 micrometers, and we can integrate so that we can generate cavitating flows, cavitation bubbles out of this probe. And we can, of course, integrate this with the use of PEEK tube, and then we can use it first and see whether it's functioning without any difficulty. So here, as you can see, we can really manipulate the probe. We can bend it around the desired angles, and at the same time we can see what's happening near the target with from the workstation we have. So we can then use this in vivo tests, and here you can see an image for in vivo tests. So we have porcine in vivo tests which were performed at the Acıbadem University hospital. We can, of course, have an access using the urethra, and we can use our probe for kind of destroying the polyps inside, of course, porcine. And you can see that here within maybe few minutes, we can destroy the targeted zone. And we can, of course, at least destroy the whole structure within maybe 15 to 20 minutes with this prototype, a metallic prototype. And we were glad that this metal printed probe could be used in vivo tests, as you can see here. And we also ensured that actuation, cavitation, and visualization systems worked properly. And here you can see histopathology results of the pathological analysis. Here we have H&E staining of the porcine tissues, and we compare it to the control sample where we do not have cavitating flows. And we have seen that the exposed air in exposed areas, we have really we can really remove material. We have erosion. However, there was no obvious damage in the area around the defect. So we were happy about the local characteristics of our approach. So this is, of course, here we have a target which is of conventional size. We can also use this approach for targets which are small. So we can really bombard a certain small target using this approach. Like we have a lab-on-a-chip version. We can, for example, bombard a single cell, for example, a cancer cell, using this approach on a chip. So we have carpet bombardment from a plane like this, but we could also use this approach for this micro scale version of this. So we can bombard a cell so that with the bubbles we can have craters on the cell, as you can see. And the size of the crater we have is close to the bubble size. So we have a breast cancer cell here, right? You can see. And upon kind of exposure for maybe few seconds, we have craters which were caused by the bubbles. So here, for example, the diameter is about maybe 3 micrometer. And using the visualization system, we can have an idea about the distribution of size of the bubbles. So the average size of the bubbles is 3 microns. So we can clearly see that the bubbles are responsible for creating craters like this. And we can, of course, test many types of the single cells, for example, different cells like this. And for example, here you can see 4 different cells, and we have also, depending on the cell type, we have different damage, different modes of damage. So this is what we have. First, we have craters. Then we have kind of damage of the membrane, and then we have kind of fragmentation of the entire cell. So we can have different modes of damage. And we can, of course, use different cells, as you can see. Depending on the cell, at the same under the same condition, we have different modes. For example, one cell is more durable, whereas another cell is less durable. So we can have this based on the damage we have. We can then see different modes here of damage on each cell. But of course, as if we have low intensity, the damage is very limited. It cannot be detected. If the intensity is too high, then we have we cannot see also anything, since we have pieces of the cell. But if it is something in between, we can really see the differences in the damage on a single cell. So we can also use this tool to characterize the properties of a single cell or tissue. And for tissues, for example, for larger samples, we can have multiple orifices, as you can see from here, and we can then have this cavitating flow from multiple orifices, and we can target, of course, a larger tissues, right, compared to single cell. So it is also possible to test them in a lab on a chip device. I think I'm almost at the end of my talk, but if you are interested in small scale cavitation and its potential applications, you can refer to our recent critical review. So here you can see the front page. In this review, we really discussed about possible applications and future research directions related to this field. I would like to thank also the funding agencies, Turkish Academy of Sciences, Science Academy, and TÜBİTAK. And this, of course, endoscopic probe, metallic endoscopic probe, was a product of our 1003 project, recent 1003 project. I would like to thank the agencies for their support, and I would like to thank the collaborators. Of course, we have collaborators from different disciplines: biological sciences, bioengineering, and mechatronics, robotics, and also pathology and urolog. Here you can see our collaborators in our research efforts in this field. And also I would like to thank my research team, the researchers I collaborated with, my students, as well as old students. And as Terin Hoca indicated, I'm also a researcher at Sunum, and our lab is located at Sunum. This is the Sunum building, and here, since it's transparent, you could directly see the lab we are working. So this would be our laboratory. And I would like to thank you for your attention. And thank you again for this nice organization.
Ali Hocam, thank you so much. This is a perfect presentation and perfect work. Thank you. First of all, I want to ask whether there are any questions from the participants. Are there any questions? Ali Hocam, I have a question. During the bombardment, those bubbles, together with those bubbles, are there any drug delivery systems at nanoscale that you use during the process for targeting, for example, the cancer cells together?
I think that's nice. Question. Yes, these bubbles could be also used for drug delivery, particularly if they are targeted to a certain field. And upon, for example, implementation of a field like acoustic field, it could be released. And we could have a combined therapy using both physical and also chemical. This is very possible, and you could even, I think, use this in lab on a chip systems and organ on a chip systems. I think it would constitute a perfect field, right? Yes, definitely.
Thank you, Hocam. Of course, there are a lot of parameters during this process. Pressure is very important, and temperature is also very important, not to disturb the tissue during the process operation. So, is it possible for you to monitor all these parameters during the operation?
We used in vitro tests. In vitro tests, it was possible, but in vivo tests, it's not very possible. And we should really repeat in vivo tests for many times in order really to control everything. Unfortunately, the number of tests is very limited, as you know, in vivo. But we made sure that it operates at least under optimum condition, as optimum as possible.
Yeah.
And from the lessons, of course, we learned from in vitro tests. But in lab on a chip systems, in the chips version of this, which I showed you before the end, it is possible. It could be possible. Yes.
Ali Hocam, thank you. I
Thank you
wish
very much.
you good luck and
very much.
successful researches for your further researches and for your future projects. Thank you that you accept our invitation and share your research with us. Thank you so much, Hocam.
It was my pleasure, and thank you very much for your efforts in this inputting and organizing this nice event. Thank you very much.
Thank you. Now, the second presentation will be held on by Associate Professor Güllü Kızıltaş Şendur from Sabancı Üniversitesi Sunum Nanotechnology Research and Application Center. Associate Professor Güllü Kızıltaş Şendur received her PhD in Mechanical Engineering from the University of Michigan, Ann Arbor University in 2003. After completion of her PhD, she worked as a postdoctoral researcher at both the Electroscience Laboratory at the Ohio State University and the University of Michigan until September 2005. She also coordinated with the Ceramic Research Group at the University of Michigan on the advanced fabrication of dielectric composites. She joined Sabancı University in 2005 and is currently an associate professor in the mechatronics program and a part-time research faculty member of the Sabancı University Nanotechnology Research and Application Center. Her main theme of research focuses on topology optimization, design and fabrication of complex engineering systems such as miniaturized mechanical, electromechanical, and biomedical devices. Over the years, she developed new material designs based on numerical simulation, schemas, and advanced fabrication methods for tissue engineering, mechanical and electromagnetic applications, with funds received from Lockheed Martin, General Electric Aviation, Marie Curie, and Tubitech. She has published numerous papers, authored 3 book chapters, and advised more than 20 graduate students, and has received the Young Scientist Award Tuba Gabit by the Turkish Academy of Science and the University Graduating Class Teaching Award. I would like to welcome Associate Professor Güllü Kızıltaş to present her research with title From Art to Part in 3 Dimensions. Güllü Kızıltaş Şendur.
Thank you very much, Tirin Hocam, for this nice introduction. And thank you very much for inviting me for this nice event. Do you hear me fine? Okay.
Everything is fine, Hocam.
Great. Thank you very much, Tirin Hocam. Good morning, everyone. I would like to present our design efforts in tissue engineering. More specifically, I want to talk about how we employ formal design techniques such as topology optimization, which I call ART, and transform them to novel material compositions for bone scaffolds using advanced freeform fabrication combined with 3D printing into scaffolds that deliver effective regeneration properties. Okay. Here's a quick glimpse of our lab located in the Nanotechnology Research and Application Center at Sabancı University, an aerial view of our campus and a nice sunset. We do work in the 3D systems modeling, design, and fabrication lab, and we make effective usage of the high performance computing center because our main expertise is on integrating multi-scale models for biomedical devices such as scaffolds. Here is the outline of my talk. I would like to start with stating the motivation in our research efforts and how it all started back 15 years ago with giving some background information on the novel material designs that we developed earlier for an entirely different application, such as electromagnetics. Then I'll state how we went from there to adapting it to tissue engineering. And I would like to present you the design framework, which is general enough to be employed to systems coming from different disciplines. And the main key idea is to focus on the material in 3D, where you can start from scratch and find the ideal material composition that delivers you the design specifications that you would like to have. I want to summarize our efforts, research efforts, in 3 groups, and I would like to go over designs that we developed using computational design techniques, present to you what we have fabricated using different methodologies, and talk a little bit about our characterization efforts using mechanical in vitro studies before I conclude and state our futuristic vision for this research. Oops, this, okay, this was a video, so this is kind of not working well, but okay. You were supposed to see the 3D layered structure first and then the scaffolds. Forgive me for this problem. But the main vision in our research group is based on the fact that for high technology devices, where it comes with many performance specifications to be satisfied at the same time, such as miniature size, large efficiency, low cost, manufacturability, and all different specifications, such as in scaffolds for the mechanical function, biological function, cell-to-cell interaction. It is fair to state that you cannot cope with these design specifications unless you have a formal, systematic way of dealing with it, and you have to deal with it on both the geometry level as well as the material level. So unlike the design efforts in the past, which were only focusing on the geometry alone, or choose whatever was available in nature in terms of the material constituent, you have to do more than that in combining your design freedom by focusing not only on the geometry, but on the material, possibly at multi-scale level. And this we did historically. We start doing that for electromagnetic applications, where we focused on the dielectric or magnetic properties, and were able to miniaturize the size of antennas and filters by 10-fold. We were able to fabricate antennas with different material compositions. And nowadays we adapt that to scaffolds that you see on top of the bottom picture, which was showing an electromagnetic device, where it's key to alter the scaffold's geometry as well as its material in such a way so that effective regeneration takes place. And there are key players such as the permeability of the material, the stiffness of the material, which is known as the mechanical property, but also the diffusivity of the material, which basically affects the angiogenesis process, nutrition delivery, as well as waste removal, among others. So it's fair to state that our biggest motivation in adapting our design techniques to tissue engineering was that in nature, or naturally, these scaffolds or well-designed scaffold implants are known or shown to be good alternatives in bone tissue engineering, and they are very useful in delivering effective healing once you take into account many functions at the same time, which presents a complicated design optimization problem. Those functions are known as biological functions, mechanical functions, and material functions, among the three key functionalities, which have a direct effect on cell attachment, proliferation, differentiation, the angiogenetic response, as well as the morphology, having a key effect on the mechanical response, such as the strength of the scaffold that should imitate and replace the actual healthy bone, as well as cell-to-cell interactions, biocompatibility, biodegradability of the material. So it's fair to say that these functionalities to be satisfied by a scaffold that you design ad hoc or in a intuitive manner by trial and error is simply not possible. And therefore, this was the biggest motivation in starting this research. Just a few words about the background of these structures that you all might be aware. The actual bone itself is a multi-scale structure morphologically, where the compact bone is stiffer than the spongy part, and the porosities have a tendency to spatially vary in space, not to mention that the multi-scale fibrillous as well as the cancellous structure is functionally gradient, what we call. On top of that, the healing process is a very complex process taking place at different time scales and different space scales with an interaction between certain proteins, growth factors, tissues, during healing, which takes place first in the form of inflammation, soft tissue formation, and hard tissue formation. So the challenge is that this process is actually multi-scale in nature, and both in time and space, and you have to accommodate for many different mechanisms coming from different physics at the same time to allow the scaffold to do its job in a very sophisticated manner and replicate the actual functioning of bone healing in the most effective way that's possible. In parallel to this observation, our early efforts showed that novel material designs through topology optimization are actually able to deliver novel response that you could not achieve using ad hoc trial and error with only the usage of available material in a homogeneous fashion. You see here examples of our earlier design schemes that were able to distribute the material. Each color code is a different material that we were able to fabricate using certain die-cast type of polymer and the ceramic, and deliver the novel response that a homogeneous substrate could not do. In literature, this was also evidence for novel material responses such as negative thermal expansion by using two available materials, the green and blue, in space in a specific geometrical orientation, such that it would deliver you a shrinking material if subject to temperature, unlike its constituents, which would actually expand as you would intuitively expect. Negative Poisson's ratio type of microstructures were actually also a result of topology optimization schemes. And back in 2005, the group of Hollister back in Michigan showed actually that this formal technique is able to deliver optimized scaffold configurations made of a single material, and that was published in Nature Materials, the concept that this can be adapted to tissue engineering as well. That took us the lead, or we took the lead in transforming our expertise in electromagnetics from structures that we designed for narrowband antennas to wideband antennas. And we in Sabancı University were able to fabricate it using multi-constituent ceramics at high temperatures. We developed the topology optimization framework in 2018 using a topology optimization based on level set schemes. I don't want to bore you with the details, but what that entails is you have basically mathematical functions that represent your material compositions, and you change the material composition or the shape and of the outer as well as inner boundaries of your bone scaffold in a systematic way using finite element analysis and optimization. Our initial framework actually was looking like the flow chart given in this slide. We were starting from an initial random design that was simply a regular hole structure which is a cross-sectional view of the 3D scaffold, and you would undergo a systematic way, an iterative way where you would update all material cells within a three-dimensional volumetric domain that you start from scratch. You have no idea what this scaffold should be looking like, but you start with a homogeneous block, let's say here, with simple holes that you can represent using level sets, and you undergo by computing the physical response in terms of mechanical and fluid flow. That was our initial attempt, and combining with certain numerical optimization solvers such as gradient-based or heuristics, where you update at each iteration of this cycle the material composition, where each color represents a different material, that until you converge mathematically, which says, okay, you do have the strongest structure with the minimum shear stress and maximum bone formation, that you hopefully can then translate using additive manufacturing nowadays or hybrid versions of those techniques to an actual working prototype that you can test further in vitro or in vivo. Our current overall objective is to expand, and we have been doing that over the years, to accommodate for the key 5 mechanisms that take into account the mechanobiological response of these scaffolds, take into account the diffusion of your cells and growth factors, as well as the angiogenic response, the growth factor release mechanism, and scaffold degradation in an orchestrated way, so that you come up with the optimal scaffold geometry that would support effective and maximum bone healing. What you see down here is essentially the a 2-step procedure to achieve that. In the first step, we do develop a multi-scale analysis framework, taking into account all of these 5 mechanisms into account. And some of these models do exist in literature, actually, and they have been worked out with experimental validation as well. We have combined these mechanisms using a finite element analysis framework and hooked it up to an optimizer. The optimization scheme looks for the optimal Young's modulus, diffusivity, and permeability, which are the key material properties of an optimal scaffold, and tries to find these in a matrix form. The second step works on top of these results, take these results and tries to do an inverse synthesis, and that's the actual novel part. It says, what should be the material composition? What should be the porosity? What should be the 3D connectedness of the microstructure of my scaffold so that I achieve these optimal material properties? Okay. And this is a more detailed version of our inverse synthesis design framework, where you have a 3-step major routine. The first step is the inverse synthesis of what geometry your scaffold should be looking like, which is delivered by a color-coded plot, with each color being a different material property with a different Young's modulus, diffusivity, and permeability. So it's easy to state that a complicated 3D composition such as this is not easily or directly manufacturable. And that's why we have the second step, which takes you from a 3D complex distribution of materials and hooks it up to reconstruction schemes, where each color is mapped into a geometry of a lattice structure. We call these gyroid lattice structures, which are known for a high surface to volume ratio, which are desired for bone scaffolds and are known in literature to accommodate for all the desired computing metrics in mechanical, thermal, and bone scaffold applications. So we transform this into a graded gyroid, we call it. So you may think about this as a gyroid structure that has varying thickness throughout this volume to match each color of the resulting design. And finally, the third step goes to fabrication of these using additive manufacturing or similar techniques that I will talk quickly. And ultimately, we test these in terms of their mechanical and biological behavior. This is one design scheme that is based not on the material distribution, but on the size of these pores, where we have combined solid mechanics and fluid flow response of these scaffolds with spherical pores in this case, and mechanobiology. We also integrated cell diffusion. You see our metrics here. We targeted maximum bone formation with certain porosity constraint and limited the wall shear stress to a value that, according to the literature, is enhancing cell attachment and is avoiding that cells would die. So effective regeneration expressed in the form of certain mathematical functions was one of the cases we were able to tackle. And this delivered us a pore size of about 410 microns. The design results of these were validated with literature by a study by Boccaccio, where you see his results in purple color, where this graph shows the velocity, the fluid flow velocity, and the x-axis shows the mechanical strain. And we were almost hands-on with those studies there, proving that the validation that the multi-scale analysis works on mechanobiology-based diffusion. On this slide, you see some recent results of the inverse syntheses. On the left, you see the color-coded plot, which calls for PCl in the red portion, and the blue portion represents pores that are transformed in a reconstructed fashion into gyroids. This is a 3D view. This is the inlet corresponding to the blue hole here in the form of gyroids, and the wall shear stress and the velocity that you would predict is within the desired range for the given metrics stated here on the left. Some other FGS functionally graded scaffold design results proved us correct, where we came up with the ideal scaffold being radially gradient, saying that the pores should be larger at the center and they should be small as 100 microns coming down to 100 microns at the top and bottom layer of a three-dimensional scaffold with square poles this time, based on mechanostat theories and taking into account also the degradation of the scaffold with time. We are currently also updating and have presented last week in Termis EU conference the interaction of the regeneration with the growth factor release and the signaling pathway interactions by coupling our current framework to additional partial differential equations to be solved using a finite element analysis model implemented in COMSOL and integrated to optimization in MATLAB. These are the results that we presented last week. The first column of data represents the concentration of the polymer scaffold made of PCl that had porous that had pores of the form of in the form of spheres. You see the mesh on the bottom right here. The water concentration with respect to time, where this is the initial state of the water concentration, the 7th date, 14, 21, and 28. We do see that the polymer concentration is undergoing both surface and bulk degradation. And sorry, I'm running out of battery. I apologize for that. Okay. And the BMP concentration growth factor release is, as expected, following a release that increases in time initially and then degrades over time, as was predicted by the reference study in Sun back in 2013 and validated recently. Now let me switch gears and talk a little bit about how we fabricate these scaffolds. We make use of material syntheses, of polymer syntheses, where we combine things with inorganics such as hydroxyapatite, and we fabricate it using additive manufacturing, as well as make extrusion using our own in-house filaments. We then, which is not being mentioned in this talk, we then collaborate with other faculty to do surface functionalization of these scaffolds as well. And what you see down here are different geometries with multi-scale porosities, both on the macro and micro level. Again, you see scaffolds that we fabricated using a bioplotter, incredible, where we made our solutions by dissolving PCl and NHA. We don't dissolve NHA. We mix PCl and NHA in a solvent and then plot it in ethanol to undergo phase separation that would induce pores at different sizes, which we analyze using our micro-CT tomograph in the Sunum in our lab. So we can basically summarize our own fabrication efforts as solution-based printing that I've just mentioned, which starts with the drawing of a functionally graded scaffold, which are less porous at the center, more porous towards the outside in 3D. We transfer that as a 3D G-code into the bioplotter and get these scaffolds in 3D. We do also filament-based printing using commercial printers such as Ultimaker 3 in our lab, with both commercial PCL filaments as well as our in-house filaments, which are mixtures of ceramics and PCL. Again, a view which shows that this is a nozzle-based solution-based printing, and we work with, as I said, PCL and HA. We use THF as a solvent and the ethanol BAT as the non-solvent. We also, I would like to note that this method has been proven to work recently also with piezoelectrics, and we're currently on the way of publishing that work as well. Characterization studies show that the morphology was well maintained using micro-CT, and that functionally graded structures that are the results of our design studies are actually delivering you an improved evidence of mechanical response in terms of having higher strength, both in compression and tension when you compare it with uniform scaffolds, demonstrating again the need for being able to design from scratch using formal methods and fabricate non-uniform and multi-material structures. These scaffolds were also characterized using SEM. You see selected images for uniform in the first row, for FGS, functionally gradient geometries that we've worked on, where both uniform and the functionally gradient scaffolds actually allowed for good cell attachment on the surface, and beyond the 21st day, they allowed arching and the formation of the tissue. Cell viability results, where we collaborate with Dr. Chetinel in Sunum, shows that the ALP activity increases steadily, and the FGS proves to be more enhancing than compared with the uniform structure. A similar trend can be observed with the NHA addition from 10% to 20%. Both the material as well as the geometry plays a role in optimizing the scaffold performance. UTM mechanical tests carried out this time on a functionally gradient scaffold delivered almost a one-to-one validation of the simulations with the compressive modulus and the strain, maximum strain performance under 1 megapascal of pressure. The similar trend was observed for the gyroid structure that we fabricated using PCL in our lab, and the compressive modulus was very close to what we predicted, with a reasonable discrepancy of the strain response experimentally that we predicted using our simulation codes. Okay, sorry. I was not using the full screen all throughout. Thank you for noting that. SEM results of the gyroid scaffolds that we carried out using MC3T1 mice fibroblasts were predicting good cell attachment and beyond the 7th day, with nice arching of cells over the struts after the 14th day, with the gyroid structure being more favored when you compare it with the uniform FGS structure that I showed you earlier. ARS and confocal microscopy results of the gyroid scaffold were also predicting nice cell attachment and growth within the gyroid scaffold that was a result of our design studies. With that, I've reached my conclusions. I want to state that multi-scale analysis-based topology optimization has the potential to deliver novel designs with multifunctionality, and I believe that it's one of the strong ways of delivering competing novel responses. At the same time, you have to undergo three-dimensional material design. Our current focus is to update our model in terms of experimental evidence and speed up studies in the computational framework, incorporate angiogenesis that we have done in 2D and we're updating it into 3D, experimental validation of growth factor release that we partially performed, but we are starting the signaling pathway interaction and bone regeneration validation. Our future focus will be on incorporating surface chemistry and nanotopography that we know have a drastic effect on bone regeneration. And we would like to update that to design of patient-specific smart scaffolds by implementing functional coatings into the modeling as well as the fabrication framework. There are a couple of references. Two of them are underway. The others are published or presented in recent conferences. With that, I want to thank you for listening, and I want to acknowledge my former students, my current students, the current and past funding, especially TÜBİTAK 1001, and my collaborators at Sabancı, Sunum, and overseas in Belgium. With that, I want to stop and would be willing to answer any questions that you might have. Thank you.
Eğer ki hayatımızda hiç eğer olmasaydı nasıl olurdu? Size şöyle söyleyeyim. Her şey daha az parlak, daha az yeşil olurdu ve daha az parlak yeşil. Çünkü eğerler ormanların derinliklerinde tek bir kibritle derinlerin kıvılcımını ateşler. Eğerler Nobel ve Guggenheim'ın aklına takılır ve o kodu bu kodu çözerler. Eğerlerle içinizden haykırmak gelir. Eğerler bariyerleri kırarlar. Asla yalnız yürümezler ve aşırı bulaşıcıdırlar. Eğerler aşikardır ve son anda golü atarlar. Eğerler dünü umursamazlar, robotlarla bile konuşabilirler. Karşı takım soluklanırken oynamaya durmadan devam ederler. Sadece basit bir kelime öyle mi? Hayır. Eğerler asla uyumazlar, hep daha fazla çaba gösterirler. Eğerler bakar, araştırır ve en beklenmedik zamanda ortaya çıkarlar. Eğerler klonlanarak çoğalırlar. Acaba gerçekten yapabilir misin? Yaptın bile. Eğerler aklınıza girmeye çalışan güler yüzlü şakacılardır. Eğerler kapıları açarlar, asla kaybetmeyeceklerini bilirler. Ve biraz gün ışığına her zaman hazırdırlar. Her şey bir eğerle başlar. Çünkü eğerler ne zamana dönüşür, ne zamanlarsa şimdi. Ve şimdi nasıla dönüşür. Nasılsa asıla. Eğerler bakış açınızı değiştirir. Eğerler oyunu değiştirir. Eğerler dünyayı değiştirir. Biliyoruz. Çünkü biz eğerlerle çalışıyoruz. Yakın Doğu Üniversitesi.
Emil hocam, you are on mute.
Do you hear me now? Yes, great. Sorry for this small glitch. Yes, good morning again. I would like to thank all the organizers of this symposium. That was very fun to listen to great presentations by our distinguished speakers, which are very experienced in their fields. I will share our humble experience in the field of 3D bioprinting during our talk. My name is Emil Mammadov. I'm a pediatric surgeon by profession, and I continue my work and studies in the field of pediatric surgery. At the same time, in 2015, it's the 7th year, we founded the new 3D laboratories under the Damrm Research Institute. And our laboratory aims to integrate three-dimensional printing with the field of medicine and surgery. So during this time, during these 7 years, we have done several works in the fields of 3D printing, and more recently, like 2 or 3 years ago, we have started working on bioprinting technology and integrating bioprinting, 3D bioprinting with the clinical trials. So let me start with my presentation regarding the current technologies for 3D bioprinting. So what is 3D bioprinting? It is utilization of 3D printing techniques to combine cells, growth factors, and/or biomaterials to fabricate constructs with the aim of imitating natural tissue characteristic. And it achieves it via precise deposition of cells / biopolymers or just cells in layers to form three-dimensional constructs. So in general, as Professor Schandemer mentioned in the previous talk, the most research is focused on the formation of scaffolds, which can hold cells and let the cells to interact with each other, both to mimic the natural characteristics of the tissue and let us do experimental research on the tissue behavior in different scenarios, or we may use those scaffolds after enrichment with cells after sufficient proliferation. We may use those scaffolds as substitutes for organs and tissues. So all the work is focused on this in this area. But what can we do to form those scaffolds? The scaffolds in past, there were many ways to form scaffolds. Different ways, different techniques like electrospinning, molding, freezing techniques, different freezing techniques were used to form scaffolds. But more recently, after the mass introduction of 3D printers in the industry, the industrial 3D printers or maker 3D printers were converted by the researchers, first by the researchers, then by the companies, to bioprinters. So to be simple, they have changed the printing heads to print biopolymers instead of just thermoplastic. So what are the main current technologies in 3D bioprinting? Actually, there are a lot of different techniques, but I will talk about the 4 most frequent bioprinting techniques, which are inkjet bioprinting. I will give a small introduction to all of them, because actually the field of bioprinting is a very broad field, and there are books written on it. So in order to fit all of it in a small time frame, I should be very precise now, and I will just give the introduction to all of these techniques. The second one is the laser-assisted bioprinting. The third one is the stereolithography. And the fourth and most frequent one is the extrusion bioprinting. So let's start with the inkjet bioprinting. As you all know, inkjet printers were first developed by Hewlett-Packard in 1970s and were patented at that time. In 1988, Kleb and his colleagues introduced a technique which uses an inkjet bioprinter, which is modified to hold biopolymer and cells. So it uses the same method to disperse cells inside the bioink instead of normal ink. So when we put the solution inside the print head or in the cartridge, we give thermal pressure, input, which creates a bubble, and that bubble is dispersed through the nozzle as a droplet, and that droplet incorporates cells, and it's printed on a flat surface, and that flat surface may be modified with a lift to move in z-axis, so that you can print cells in layers. There are 4 main approaches for inkjet bioprinting. The first and the most ancient one was the thermal one, the most frequent one. We have also piezoelectric actuation. We have acoustic inkjet 3D printing techniques or electrostatic inkjet 3D printing techniques. All these techniques vary, do the same thing, but vary in the effectivity and different techniques affect different the cell viability. So, for example, in thermal 3D printing gives more thermal damage to the cells than piezoelectric one. But as the thermal damage, thermal input is less than a second, so most of the cells within the ink still survive. So it's still used technique. However, there are some disadvantages of this technique, like nozzle clogging and inability to use high viscous materials. The second type of bioprinting, and the most expensive one, is the laser-assisted bioprinting. This is a very interesting technique. Here we don't have any nozzles. We have a ribbon, we have a pulsed laser source, we have a laser focusing tool, and there is the laser pulse hits the ribbon and forms again a bubble, and that bubble drops onto the substrate, receiving substrate. And when you do it in a fast and precise manner, you may form constructs. This is the most precise 3D bioprinting technique, and it also eliminates the need of nozzles, so it doesn't have a disadvantage of nozzle clogging. At the same time, it may print at micro scale, so at the micron scale, different from other techniques. However, it's the systems that use this technique are very expensive. The companies which produce this are very scarce, and the printers, the bioprinters which use laser-assisted bioprinting are very expensive. The other type is stereolithography. Stereolithography method actually is the first 3D printing method that was developed. It was actually developed in 1980s, and it was the first 3D printing method that was published. After that method, the fused deposition modeling method came, which we all use now. But stereolithography is the first method, and it used in normal systems, in industrial bioprinters. Stereolithography, SLA printers, use special photosensitive resins, which are cured by a light source, UV source, and when this light source is shines on the photosensitive resins in layer, it forms layers, and it's the only bottom-up approach in 3D bioprinting. However, SLA 3D bioprinting, actually DLP, digital light projectors. We don't use lasers, but we use digital light projectors here. It's a more recent method. It's a very precise method. There are two main disadvantages of this method. There are only 2 or 3 photosensitive biocompatible resins that we can, biocompatible materials that we can use here, which are gelatin methacrylate and PEGDA, polyethylene glycol diacrylate. So the material scarcity is the main disadvantage of this method, and UV, the curing of the material with UV also may negatively impact the viability of the cells. However, some studies show that even this method may maintain high viability of the cells if used with appropriate UV Now we come to the most frequently used technique, which is extrusion bioprinting. Extrusion bioprinting is actually a method where we changed our 3D printer nozzles to syringe barrels. We put our bioinks with the cells or without the cells inside those barrels, and we applied either mechanical force, air pressure, or screw-driven, or microvalves to push that bioink onto the build plates. Generally, we use Petri dishes as the build plates here. So this is the most cost-efficient and the fastest way to make three-dimensional constructs. Professor Schandemer have shown you their the printer that they have used, the Incredible by Selling, and the printer which uses the pneumatic pressure to dispense the cells and the bioinks. So as you see here, the most recent research in all the tissue engineering applications, most frequently used method is the extrusion bioprinting method. So as you see here, the photos from our bioprinter and our scaffolds, you can form tissue scaffolds or scaffolds for experimental research on Petri dishes inside this enclosed machine. Recently, we removed the enclosure and put the machine inside the biosafety cabin. So I'll show you the video of our printer in work. You may form different by changing the nozzle size and changing the G-code. You may print different scaffold types. These machines are not as precise as laser assisted bioprinting or stereolithography bioprinting, but they still do their work, as you see. Of course, you have to be very well aware that these machines are not plug-and-play machines. You have to be very confident in G-code knowledge. You have to know what slicing is. So without proper 3D printing experience, it's extremely hard to handle these machines. So you see here we are printing different patterns as Professor Schandemer managed. This is a honeycomb pattern. The previous ones were rectilinear pattern. We showed some hollow structures printed. These all are printed in our test gels. However, we also use gelatin and alginate and gelatin alginate, and also Professor Terina Dalle provided us with her alginate ketozan hydrogels to try out in these machines. As you see, this is a gyroid pattern that we are printing now. The prints are all done inside the sterile chamber and by sterile nozzles using sterile syringes. Of course, you may also print not only the scaffolds, you may slice the tomography or MRI images to print exact structures fit for the patients. This ear structure was segmented from the CT scan and printed on our machine using hydrogel provided by Professor Terin Adalı. And I am very proud of this picture. I will stop by here and thank you very much for listening to me.
Eğer ki hayatımızda hiç eğer olmasaydı nasıl olurdu? Size şöyle söyleyeyim. Her şey daha az parlak, daha az yeşil olurdu ve daha az parlak yeşil. Çünkü eğerler ormanların derinliklerinde tek bir kibritle derinlerin kıvılcımını ateşler. Eğerler Nobel ve Guggenheim'ın aklına takılır ve o kodu bu kodu çözerler. Eğerlerle içinizden haykırmak gelir. Eğerler bariyerleri kırarlar. Asla yalnız yürümezler ve aşırı bulaşıcıdırlar. Eğerler aşikardır ve son anda golü atarlar. Eğerler dünü umursamazlar, robotlarla bile konuşabilirler. Karşı takım soluklanırken oynamaya durmadan devam ederler. Sadece basit bir kelime öyle mi? Hayır. Eğerler asla uyumazlar, hep daha fazla çaba gösterirler. Eğerler bakar, araştırır ve en beklenmedik zamanda ortaya çıkarlar. Eğerler klonlanarak çoğalırlar. Acaba gerçekten yapabilir misin? Yaptın bile. Eğerler aklınıza girmeye çalışan güler yüzlü şakacılardır. Eğerler kapıları açarlar, asla kaybetmeyeceklerini bilirler. Ve biraz gün ışığına her zaman hazırdırlar. Her şey bir eğerle başlar. Çünkü eğerler ne zamana dönüşür, ne zamanlarsa şimdi. Ve şimdi nasıla dönüşür. Nasılsa asıl. Eğerler bakış açınızı değiştirir. Eğerler oyunu değiştirir. Eğerler dünyayı değiştirir. Biliyoruz. Çünkü biz eğerlerle çalışıyoruz. Yakın Doğu Üniversitesi.
Yes, due to power outage in North Cyprus, I couldn't join the broadcast, but now generation kick in and problem solve, and we will continue. Now, I want to thank Associate Professor Dr. Güllü Kızıltaş Şendur for her perfect presentation, and I want to thank Associate Professor Dr. Emin Mamadou, also our colleague from nearest university, Damrm Institute, for his presentation. And we will continue with Associate Professor Dr. Özay Öneral from nearest university, Faculty of Dentistry. Özay Öneral started the undergraduate program of dentistry in 2009 at the nearest university. After 5 years of well-equipped education, he graduated in 2014 as the valedictorian. He focused on computer-aided manufacturing technologies in doctoral study and earned his PhD degree in prosthetic dentistry from nearest university, Health Sciences Institute. He is currently working as an associate professor in the relevant department. He has been working as the Vice Dean of the Dentistry Faculty since 2021. Additionally, he is the coordinator of the undergraduate and doctoral level courses on 3D fabrication technologies. He served as General Secretary and Scientific Affairs Delegate in the Turkish Cypriot Dental Association. He has manifold publications in prestigious SCI and SCI Expanded Index journals on topics such as material science, three-dimensional printing, additive manufacturing, and subtractive manufacturing. And he took charge of many symposiums and congress targeting the aforementioned topic. He still works on the reviewer and editorial boards in esteemed journals. Now, it's an honor for me to invite Associate Professor Dr. Özay Öneral for his presentation titled 3D Printing, Discovering the New Horizons in Dentistry. Please, Professor Özay Öneral.
Thank you very much, Dr. Nadal. I want to extend my appreciation to you, University, for inviting me to participate in such a great symposium. I don't want to wait all the auditions over here. Let's go ahead. Let's get started with our presentation. Dear participants, welcome to the session on rapid prototyping methodologies used in contemporary dentistry. In this session, dear participants, I'm going to try to give brief information regarding the developmental process of fabrication methodologies, fabrication rows, formative technologies, bioprinting principles from the perspective of a dental practitioner. In the computer-aided design, computer-aided manufacturing technologies, which initiated with the mapping of intraoral tissues in 1977, rapid advancements have been experienced, and today 4D printing, bioprinting opportunities have come to the fore. The application of computer-aided design and computer-aided manufacturing in dentistry has progressed ever strongly over the past few decades, and it has led to the fast diversification of the materials and to the digitization and automation of the process. The first step in the digital workflow is the digitalization of the relevant zone by acquisition of a great number of images with the aid of either intraoral or extraoral scanning technologies. Subsequently, computer-aided design of the relevant part is performed by using inbuilt software. 3D CAD file is usually available in the standard tessellation language file format or the standard interface. And in conclusion, computer-aided manufacturing process is conducted by using different roles. We're going to discuss these roles in the next slides. Here you can see the digital workflow that the dental practitioner usually follow. As I said previously, at the very last stage, standard tessellation language file, or the virtually designed part, is sent to the computer-aided manufacturing machine for fabrication. And the CAM process, CAM software, cuts the STL file into multiple horizontal layers, I mean XY plane. This is so-called slicing issue. And the different slices contain the path information like X, Y coordinates. The result of the slicing is the so-called G-code, which contains the machine command for the printer. Thinner film thicknesses are associated with the smoother objects, but also a longer printing time. This is the principle that we have adopted in 3D printing and also the computer-aided manufacturing technologies. Let's go ahead with the fabrication roads in the next slide. You know what? Until recently in dentistry, the CAM process was synonymous with the subtractive manufacturing process. And they said not computer-aided manufacturing, computer-aided milling. And in this process, an object is created out of a blank or block by milling or grinding or drilling by using specific tools like computer-commanded burrs. Alternative ways of producing CAD files are the additive manufacturing processes. All additive manufacturing processes have in common that on the basis of 3D design data, the physical properties, the physical object is built up by the sequential application of the material. I mean layer upon layer. In addition to the term additive process, the synonymous, the generative process, the rapid prototyping, and 3D printing are often used. In subtractive road, a significant amount of residual waste material is generated at each time, unfortunately. And again, this waste material cannot be recycled actually. From a procedural and ecological point of view, subtractive production has the disadvantage in that the surface resolution is unfortunately limited by the smallest tool radius. And also the subtractive technique has a limitation with regard to the number of objects it can produce per machining, per operation. and it's not capable of reproducing more complex or sophisticated geometries, unfortunately. Furthermore, the tools used in the fabrication process shows the signs of wear or abrasion after repeated use, which can lead to mechanical complications in the parts produced, unfortunately. So let's go ahead with the additive technologies, because they have done a novel technology, especially in the dentistry. In additive road, a very limited amount of waste material is generated at each time, and this waste material can be recycled. That's a good news. Also, complex, sophisticated geometries with very fine details and higher accuracy can be produced with this road. However, in this road, staircase effect and bowling effect are the main concerns that have been encountered by the clinicians or the operators. Let me give brief information about these effects and then go ahead with the next slide. Stair type effect, I mean in the layer upon layer fabrication in the additive method, creates rough surfaces in the final product at the corners especially. And this phenomenon is called the stair type effect, because these rough surfaces, as you see in the slideshow, these rough surfaces look like actually stairs. And you can handle this procedure by reducing the layer thickness to the smallest possible value. You can significantly reduce the incidence of this effect by this way, but don't forget that it should be noted that the fabrication time will increase significantly with this method. Let's go ahead with the bowling effect shortly. It's a common failure in additive techniques. If I'm going to give a name of an additive technique specifically, I can say selective laser melting. We're going to discuss later on this topic, but in the bowling effect is a common failure, especially in the selective laser melting. This phenomenon can increase surface roughness, reduce density, cause pores in the final product, and in severe cases even hinder the fabrication process. The bowling effect occurs when the molten particles cannot wet the underlying material layer due to the surface tension, and it in turn separates the liquid particles, unfortunately. And several factors should be considered regarding this effect, like high scanning speeds combined with the high laser output powers should result in less bowling effect, for example. Not only previously mentioned effect, bowling effect and staircase effects, but also the building orientation can influence the accuracy and surface characterization of the objects that you are going to produce. The orientation of the objects on the building panel, especially in the Sla technology, I mean stereolithography, and we're going to discuss this later on, is another variable that can influence the printing result with regard to accuracy and mechanical properties. They have done lots of studies on it, and one of the favorite studies that I would like to mention to you over here is Al-Harbi and et al. Have done a study and found that an angle of 135 degrees to the building platform to the most accurate. Also, they have proven that vertically printed temporary materials showed significantly higher compressive strength than the ones, the horizontally printed materials. Let's get started with the technologies. As you can see in the current slide, additive techniques can be classified into three main categories. Broadly categorization, in accordance with the material used, the state of the material, can be solid, can be powder-based, or can be liquid-based. And manifold techniques are in use and adopted, and most common ones in contemporary dentistry are Sla technology, stereolithography technology, fused deposition modeling, and selective laser sintering, respectively. You may ask in which departments they are most common, the 3D printing technologies, but I can say that almost in all departments, like prosthodontics, orthodontics, surgery, in every single department, most probably we are using 3D printing advancements, applications. And let's get started with the stereolithography. Sla is most probably first commercially available 3D printing technology. This rapid manufacturing method involves photo-induced free radical polymerization to create layered structures by using highly cross-linked polymers. The exposure of the monomer activates the polymerization reaction, which stops locally due to the solidification and limited movement of the free monomers. This technology may be subdivided into different categories, like in accordance with the platform motion, I mean ascending motion or descending motion and laser movement. The prominent features that you may encounter for the SLA is high resolution, accuracy, rapid fabrication with very smooth surface details, able to create complex, sophisticated particles with very fine details, and it's a nozzle clogging can be avoided in this technique also. All these things make SLA as a good choice in dentistry with a plethora of material options, namely acrylates, plastics, and ceramics we can use in the fabrication of lots of appliances. We can use all these materials with the aid of SLA technology. Definitely, the accuracy of SLA fabricated products is very critical, and it depends significantly on the curing depth of the polymerization, which is described by the Beer-Lambert law, as you see in the slideshow. Moreover, the extinction coefficient K depends on the intrinsic properties of the resin, which includes the loading fillers, the surface of the fillers, and the refractive index of both fillers and the resin. You may ask why I'm trying to explain such formulas and making all the procedures complicated, but this stage is very critical, guys. If there is a mismatch in the refractive index between the fillers and the resin, the laser light will be scattered significantly, resulting in a reduced polymerization depth. And this effect can result in a previous layer not connecting to the next layer. And you can encounter routinely delamination of the stages, delamination of the layers, unfortunately. And why this is important? This is very critical, and this plays a critical role in the material preference. I'm going to show you a slide in the next slides. I'm going to explain what I'm trying to explain, why it is so critical, the material preference in this point. Previously, yttria stabilizer has been blended with acrylates, photoinitiator, agent to create an homogeneous hybrid sol, and this ink can be photopolymerized by a light curing capability, which is called technology. Also, SLA was used for printing not only the dental bridges, but also zirconia implants. You may ask, titanium option, we can fabricate titanium very appropriately with other techniques like SLS or electron beam melting. But you may ask why zirconia implant is so important for you. Zirconia implants are very important for us because they provide a superior service in terms of aesthetics, especially in the patients presenting very thin gingival biotype. The titanium implant appearance, opaque appearance, and if there is a very thin type over there in your patient, this may reflect underneath issues, causing an anesthetic of there. And you can fabricate with SLA technology the zirconia implants. That's brilliant. Accommodates flexibility in design, geometric shapes, scaling, resulting in highly accurate personalized devices. For instance, the use of the SLA printed drilling templates to transfer virtually implant planning into reality has become as a standard fabrication method with navigated implantology, and is superior to other procedures like milling, for example. Although SLA printed dental devices suffer from poor mechanical strength, incorporation of the nanoparticles into the polymeric matrix to increase its strength actually. As I mentioned in the previous slides, material preference is very critical, which influences the long ability of the product that you have produced. You can see the table in the slideshow. Have a look, please. That all guys were fabricated with the SLA technology. Only the difference is the material option, material preference. And have a look to the alterations. For example, in the flexural strength values, 50, 80, 90, and you can understand from this point of view that changing the material type will alter your mechanical or surface or all other characteristics, although doing all the procedure with the same SLA technique and machine. SLA is also beneficial in the fabrication of castable patterns, which are helpful in the fabrication of prosthetic restorations. I mean, both temporarily or permanently fabricated restorations. We can fabricate these all restorations with subtractive rod, definitely, but we are coming to a point that we are talking about large amount of waste material of the procedure. Unfortunately, I'm talking for the subtractive manners. That's why it's more beneficial to use this technique for the fabrication of the temporary or permanent crowns. Trays also for conventional impression procedures can be accurately fabricated with the SLA technology. SLA not only for the tray but also can be safely used in the fabrication of the study or master models of the patients as well. Traditionally, we use gypsum models in dentistry, which can deform day by day. You are shaping it, or it can hit down, and basically it can be deformed easily. It cannot able to protect its dimensional accuracy actually. However, the durability and dimensional accuracy of these SLA fabricated models, as you see in the slideshow, is definitely superior than those of gypsum models. Let's go ahead with the second technology. It's quite similar with the SLA technology, but DLP, the digital light processing technology, is quite very little different from the SLA technology. A microsystem, angular mirror, namely digital micro mirror device, and the micro mirror has light switches project the light from the source as individual pixels onto the projection surface. Resolution of the projected image definitely corresponds to the number of these mirrors. And the most prominent feature of the DLP technology is that every layer can be cured with a single shot, guys, and a single shot of laser exposure. Not definitely expose all the layer point by point by point like we are doing in the SLA technology. Here, one shot and all layer cured specifically in a single minute. All layer can be cured individually. We can produce complete dentures with the DLP technology. I mean, base of the denture, it can be printed with the DLP. And in the current slide, you can see a proof of concept of the technique. Here, the previous slide, how they can produce the complete dentures with the aid of DLP technology. Root analog implants are with the aid of DLP technology, but it's so experimental and they are still working on it. DLP, like we are doing in the SLA technology, DLP can be safely used study and master models of the patients as well. I said it, SLA and DLP are quite similar to each other, but they have small differences between each other. The main difference is the light source, definitely. SLA benefits from ultraviolet laser beam, while DLP uses again ultraviolet, but from the projection source. Consequently, in SLA, laser beam moves from point to point and cures the resin from. But in the DLP technology, the light source is stationary and cures each layer, as I said to you in the previous slides, cures each layer of the resin at a single time. Definitely, if you're talking about the rapid production, DLP gives you very good result. You can rapidly produce, extremely rapidly produce what you want with this technology. About details, if you're talking about fine details, I mean accurate parts with intricate details, at that time I definitely recommend your SLA technology to fabricate your product, because it gives much more, it presents much more accuracy to you, much more fine details to you. Sls technology is another one that is so common in dentistry and allows the creation of 3D models by consolidating consecutive layers of powder and the metallic powders. In this method, a laser beam, commonly carbon dioxide laser or neodymium doped yttrium aluminum garnet laser, can be used with a controlled PET scans to sinter, or to partially melt it by heating. We are not completely melting the metallic powder in this technique, because we have another technique that we're completely melting these metallic powder, which is called selective laser melting technology. We're going to discuss it later on. But over here, please focus not completely melting all the metallic powder in this technology. High power of laser allows the fusion of powder through molecular diffusion, guys. And after scanning, the powder platform is lowered by a single layer, typically 20 or 100 micrometers in most of the devices. It can be changeable in accordance with the device. And a new layer of powder is dispersed on the platform, again cured by the exposure of the laser, and the process is repeated, whole process is repeated until the completion of the 3D model. This technique, I said it, is very popular in contemporary dentistry, specifically in the fabrication of metallic guineas, as you see in the slideshow. For instance, frameworks of the hybrid prostheses, frameworks of the removable partial dentures, metallic scaffolds, and titanium implants, all we can do with the Sls technology. The temperature applied by the laser throughout the process should be kept well below the melting point of the metallic powder, and the heat should be sufficient to sinter the particles of the material. The material is not completely melted in this technology. I'm repeating again and again. Only sintered, guys, which saves a lot of time during the fabrication. Have a look here. That's a very important article that I have found lately. In particular, hybrid processes like 014 processes that we named them, produced with Sls technology, suffer in terms of weight. And for this reason, the metallic infrastructure of the hybrid processes has started to be produced with the approach expressed as the truss effect, which is evacuated and combined with the triangular connections in its inner structure. And in new studies, they have investigated these production style. And the good news is that there is no loss of mechanical properties, mechanical features of the prostheses produced with this approach, but the weight of the prostheses significantly decreased, guys. I want to extend my appreciation to Dr. Tolga Pekperdachi for sharing this case with me. He investigated this issue that I mentioned in the very last slide to you, and he checked the weights of these frameworks with the Sla technology. However, in one of the framework, hollow design with the truss effect has performed, and please check out on the side the weights of these two frameworks. Both are Sls fabricated. Main difference is one is hollow with fabricated with truss effect, and the other one is with full density. And check out prostheses. SLM, another one, and can be taught as a variation derived from the Sls technology, because the same steps are applied in both techniques. I said to you that the main difference is that SLM completely melts the metallic powder particles with the powerful laser beam, and melt pool is formed. Thus, at the end of the production phase, metallic parts with almost 100% density and superior mechanical properties are obtained without the need of any extra processing or post-processing. Moreover, it is advantageous to carry out the process under inert gas, since the liquid metals cannot wet the surface actually because of the surface oxide films. However, quick fluctuations in the temperature, I mean changing state quickly from solid to liquid and then liquid to solid, this can cause a little bit mechanical complications, namely stress accumulation on the product, or distortions, or shrinking, cracking, or maybe balling effect. You remember at the very show I have described you and tried to briefly inform you about the balling effect. And the balling effect is commonly encountered in the selective laser melting technology, as you see in the slideshow. Likewise, in the selective laser sintering, in selective laser melting as well, we can produce frameworks of hybrid prostheses, or frameworks of removable partial dentures, metallic scaffolds, implant parts, I mean abutments, for example. We can produce all these things with the aid of selective laser melting technology. In our very recent study, it has been proven that SLM fabricated implant frameworks exhibited superior fitting accuracy, and SLM technology can be recommended as an alternative way for the implant framework fabrication. There are lots of, we have discussed some of them in And we have also traditional golden standard fabrication roles like casting, but SLM is coming forward with all these properties. In another fabrication way I'm going to talk about now is electron beam melting. Typically, selective laser sintering, selective laser melting, and electron beam melting are quite similar to each other. But in this device, we are not using laser actually. In this technology, in the device, electron beam gun is located at the top of the vacuum chamber, and the operation starts with sending an electron beam from the filament. A series of coils is used to control and scan the bundles, and by accelerating the electrons between the anode and cathode ends, the energy required for the melting of the powders is generated, is produced. And using electron beam instead of laser is the main difference. And again, I'm telling to you, is the main difference between electron beam melting and selective laser melting, selective technologies. Electron beam melting, unfortunately, has a single material option. I mean metals, metallic powders. But it is a good choice for the fabrication of the dental implants, as you see in the slideshow. Here again, the electron beam melted printed mandibular, partial mandibular, I mean lower jaw, part of lower jaw, was implemented rehabilitation of the effect, as you see in the slideshow. And there are a number of studies targeting the electron beam melting fabricated implants, dental implants, as you see in the slide and also in this slide. They are working on it. It's experimental, but good results are achieved with this technology in the fabrication of the dental implants. Is another commercially available, specifically in dentistry, commonly used in dentistry actually. In the FDM technique, also known as the fusion filament fabrication, has a widespread use among AM technologies due to its relative inexpensiveness, high speed, simplicity. Everything can be supplied with the aid of fused deposition modeling. This technique depends on the deposition of the thermoplastic material actually in semi-liquid state throughout producing a nozzle that extrudes material in a specific path to form layer upon layer, actually a 3D model. And the extrusion head hits the material. The thermoplastic material is a strict shape and comes through, and when the filament gets hotter, it melts it, but not actually at the high level, because when it touches to the platform, completely stops the melting procedure and make it set actually, when it immediately touches to the platform. The molten viscosity has to be high, be it structural support during the fabrication, also low enough to allow the extrusion. You remember that the nozzle clogging cannot be achieved, cannot be encountered in the Sla technology. But this is a nozzle-based technology, and this can cause nozzle clogging. That's why the heat, the temperature of the molten thermoplastic material should be adequate, should be appropriate to support and also not causing a clogging effect, unfortunately. Multiple nozzles are available in contemporary dentistry. You can print with the multiple nozzles and also with multiple covers actually. Currently, it is feasible to fabricate custom trays for the impression procedures with FDM technology. And now we come to the point we talk about the fabrication of polyether ketone medical implants with FDM technology. I said that various experimental studies are carried out on the fabrication of the ceramic restorations with the FDM technique. It's mechanical and these are not sufficient, unfortunately. This technique have revolutionized the fabrication of restorations. It enables the production of a large number of temporary restorations very quickly, and this has changed dentistry because no more the other technologies are able to use for the fabrication of the temporary restorations. FDM is doing its best in this area, in this road. For this purpose, I mean, FDM is taking further towards becoming the golden standard of the temporary restorations. Like in the DLP technique, complete dentures also can be fabricated with the aid of FDM technology. The technique that I want to mention you today is photopolymer jetting. In photopolymer jetting, the light-sensitive polymer is jetted through into a building from an inkjet printing head and cured again layer by layer on the descending platform. The most outstanding feature, we can the technologies I have described, outstanding feature of this, you can produce with rubber-like materials like silicones, and this makes also, I mean 16 micrometers, and with this opportunity makes the photopolymer the best candidate to be used in the fabrication of the maxillofacial prostheses. Also, multi-cover jetting is available in this technology. However, the bad side is that, the drawback is that only resins, waxes, and the silicone-like rubbery materials are available in technology currently, unfortunately. I want to show you that, I mean, you witness the developmental process of the materials used in the fabrication of the maxillofacial prostheses, and also the techniques used in the maxillofacial prostheses. I put it over here because I said it in the previous slide over here that photopolymer jetting is a good best candidate maybe for the fabrication of the maxillofacial process, because multi-jetting is available, multi-cover is available. Again and again, I'm telling you, can fabricate the maxillofacial process with other technologies like SLA or fused deposition modeling, as you see in the right-hand side slideshow. Over here, I have reinforced all the previously mentioned dental implementations of 3D printing with scientific studies. We technology in dentistry. It's not like roughly or trying to try something to find to be used in dentistry. They're actually scientific, and we are completely in 3D printing. And that's very good news for us, because we can produce customized, we can produce very accurate and in a very short time good products actually, which is important especially in dentistry, to provide and also mechanically sound generating restoration to a patient in a very short period of time. That's the most critical thing in dentistry actually. Let's go ahead with the 4D printing. Okay, we have finished 3D printing, but the main topic is that actually in 3D printing and the 4D printing. 4-dimensional printing adds the time dimension to the 3D printing actually, by producing pieces made of bio-oriented smart materials, as you see in the slideshow. 4D printing indeed combines 3D printing with the use of responsive materials that change their properties or shapes or stimulus to the mechanical, chemical, maybe electrical stimuli. Materials that may be divided into shape memory materials and shape changing materials. Shape memory materials derived from the alloys, polymers, or ceramics, and each material has advantages and disadvantages, but I have very limited of time today over here. That's why I'm not able to explain every single material to you, unfortunately. I want you to know that we have lots of material options that we can prefer in accordance to their physical or mechanical properties, also biological properties. And it has our own advantages and disadvantages. Shape memory polymers have applications in dentistry, including orthodontics, endodontics, prosthetics departments. Let's have a quick look on these. One of the most common materials used in orthodontics is nickel titanium arch wire. Many advantages and disadvantages. Some of the drawbacks of shape memory arch wires may be overcome, may be circumvented with the application of the shape memory polymers actually. Superior aesthetics improved elastic modulus, enhanced mechanical and dimensional stability, and also ability of the arch wire to adapt or self-adjust during the treatment actually, make the application of this material more suitable for the patient and also dental practitioner as well. Endodontics again is another field that may benefit from the 4D printing actually. One of the most patients encountered during the root canal treatment is instrument separation, and the ability of the shape memory metals to adapt root canal cavity or curvatures of the root canal is an important asset that makes them competitive as a replacement of the traditional nickel titanium rotary instruments actually. What about prosthodontics? It's my department, and I want to mention a little bit things about the prosto as well before finishing my presentation today. In prosthodontics, permanent seating of the breech pontics, as you see in the slideshow, photographs, illustrations, while surrounding hard and soft tissues are undergoing changes, may result in suboptimal fitting of the pontics actually. Of shape memory polymers materials in these restorations may be beneficial because of the self-adjustment capability of the material, and also full or partial removable dentures. After the loss of natural teeth of the patient, we can encounter with the bone loss actually in the complete or partial dentures, partial edentulosins. And after this, it goes ahead to lose its oven. I mean, the bone can lose its oven actually. And this bone resorption can be fixed in a manner maybe of 4D printing actually. Denture relining actually is a common procedure to fix all the things undergoing the complete denture. And if you use shape memory polymers for the 4D printing of the complete dentures, despite of the bone resorption, it may change or it may with the aid of these shape memory polymers. No more needing for necessity for the denture relining. Let's talk about later at the last about bioprinting and then finish the slideshow. Numerous attempts have been made on the 3D 4D print, 4D bioprinting, I mean, to develop all cell-based artificial teeth, confirming the possibility of artificial regeneration of teeth and also surrounding tissues like alveolar bones or periodontal lips. Scientists have several difficulties, and with the aid of bioprinting technology, they are able to construct all the layers, maybe all tissues, with the aid of multiple types of living cells, biomolecules, and biomaterials. But it's not enables the regeneration of tooth-like composite tissue, but can also precisely control the shape of regenerated by using medical imaging data from the patient. But I said again and again, it's a very hot topic, it's very experimental, and it's a conflict of interest. All the experiments are trying to replicate bioreplication of the tissues that we are familiar in dentistry, like cement or dentin or enamel tissue, or maybe even pulp tissue, soft tissues. But they are so experimental. They are trying, and hopefully in 2 or 3 years, we're going to get the results of these amazing studies of the scientists. Thanks for your attention. I hope you are not bored, dear participants. Do not hesitate to forward your comments or criticisms or questions to me. I'm ready to answer.
So much for this wonderful presentation.
Thank you very much.
Are there any questions from the participants?
Yeah, if there is any question, I can see in the chat. Let me check it out. I think there is no, dear Dr. Turin. If you
Hocam, I have one question.
Yes.
Now, I think one of the important problem in dentistry is the jawbone problem during implantation. So,
especially temporal mandibular joint problems. Yeah.
Yeah. Is there any possibility to design dental implants that trigger the regeneration of the jawbone? For example,
Yeah, I have encountered lots of studies about this topic, but I said before, at the end of the studies, I mean in the conclusion section, that we are trying to fabricate something, but it's not maybe ready to be used in dentistry because it's so experimental. But I have seen a successful biofabrication of the temporomandibular joint parts in the studies, but I didn't actually encounter with the complete mandibular jaw implant actually. I have seen one, but it's not bioprinting actually. It's replicating the tissue, bone tissue, to give an aesthetic appearance for the patient because of a mandibular deficiency. It has been extracted, unfortunately, for the patient. They have done this, but I didn't even see any study during presentation. I'm searching for lots of studies on this topic, but I haven't heard anything about completely 3D bioprinted fabricated mandibula, I mean lower jaw. But maybe research will be in the future.
thank you so much, Ojam.
You're
Thank
welcome.
you.
You're welcome. Thank you. Bye-bye.
And also, I want to thank you that you accept our invitation and present a very valuable topic to us. Thank you. Now, the next topic is related with the tissue engineering, and Associate Prof. Dr. Eileen Schandemer from Ege University Department of Bioengineering is going to join us. Eileen Schandemer graduated as a mechanical engineer from Boğaziçi University, Istanbul, Turkey in 1994, received her Master of Science degree from the Institute of Biomedical Engineering from Boğaziçi University in 1997, and her PhD degree in Material Science and Engineering from University of Illinois of Urbana-Champaign, USA. She is an associate professor at Ege University Bioengineering Department, Izmir, Turkey, and is currently the principal investigator of Ege Research Group of Biomaterials and 3D Biointerfaces. Her research interests includes interactions of animal cells with biomaterials, tissue engineering, mechanotransduction, stem cells, and biocompatibility testing. She is particularly interested in design and production of in vitro tissue engineered 3D personalized disease models for pharmaceutical screening and minimizing animal testing. Associate Professor Eileen Schandemer is among the founding members of Turkish Biodesign Team. She has co-authored more than 30 scientific papers, 3 patents, and 5 book chapters. It's an honor for me to invite her to present his presentation with title Optimization of Cell Viability in Bioprinting.
Thank you very much, Terin Hocam. Can you see my presentation well, and can you hear me well?
Yes, Hocam. Everything is perfect.
Okay, thank you. Thank you for this nice introduction, and thank you for inviting me for this event, Terin Hocam. And I will try to share with you some of our experience on bioprinting. And please excuse my voice. I'm still recovering from COVID. I have, after 2.5 years, I became infected with COVID too, and had been at home for the last 1 week. So my noise is still a little bit unpleasant. So I'm sorry about that. Today, I want to emphasize what is bioprinting. Actually, Emil Hocam has given the definition, but I want to I will not repeat what he has already said, but I want to emphasize, because the term is misused, or 3D printing and bioprinting, it is used interchangeably from time to time, even by the people that are actually in the field. When we say 3D printing, we mean all of the different manufacturing techniques that have been mentioned since the morning, and they have different approaches, and even improving a lot of new techniques for 3D printing. But when we say bioprinting, it's a subset of 3D printing. Of course, we are using 3D printers for bioprinting, but they are specialized 3D printers. And actually, when we say bioprinting, we're talking about bioinks, which are composed of materials plus live cells, or at least some biological molecules like different proteins or polysaccharides that are delivered within the material. So those bioinks, living inks, are printed using different approaches of 3D printing when we talk about bioprinting. Well, Emil Hocam had given an introduction of different types of bioprinters. I will not repeat what he has already said, but I just want to point out, going from inkjet printing towards laser printing and extrusion printing, we're losing some speed. So as we go from inkjet to extrusion bioprinting, the high throughput or the speed of printing decreases tremendously. That's why the most commonly used form of bioprinting, which is extrusion bioprinting, is not a fast process. But looking backwards, why is it most commonly used? Because from going again from inkjet to extrusion bioprinting, we do have higher cell viability and higher cell density. So that's why in terms of bioprinting, we're trying to print alive parts. In 3D printing, we do produce the scaffold first, and then we can seed, if we want to, cells on those scaffolds. Güllü Hocam, for example, in the examples that she had provided, they were producing the scaffold and then seeding the cells on those scaffolds, 3D printed scaffolds. In that case, because printing and cell seeding is performed separately, we don't need to worry about cell viability. But while if we're trying to print the live bioink itself, printing process becomes much more harsh, much more prone to lowering cell viability. That's what I will try to emphasize during this talk. With inkjet printers, as I have already said, and even actually Emilia Hoca has already said, that they are the fastest. But because they require very low viscosity, because it's like the inkjet printers that we used to have actually when 15-20 years ago, until 15-20 years ago. But we use very low viscosity inks. So therefore, the amount of cells that can be incorporated in those inks are limited. So therefore, it's difficult to print 3D vertical structures that are loaded with cells. And laser-assisted bioprinters are relatively higher resolution and higher viscosity, so more suitable for printing cells, but they are relatively high cost. And also, we're using heat from lasers, so that heat may damage also cells when we're trying to print live cells. So therefore, the most commonly used type of bioprinters are extrusion type bioprinters, where in this case we do lose a lot of speed, but we can carry the cells using different types of gels, and within those gels we can load quite a lot of amount of live cells or proteins or other biological molecules if we need to. That video, again, you have seen similar videos, so I'm not gonna have it played. When we look at biomaterials for 3D printing, actually this is probably the reason why 3D printing and bioprinting is used interchangeably. We can use different biomaterials for 3D printing. The fact that the material will be used inside the body doesn't mean that it's bioprinting. For example, calcium phosphate bone cements are very commonly used biomaterials that are used in a lot of implantation applications in the body. But usually these calcium phosphate bone cements, although can be 3D printed, as there are a lot of examples in the literature, they are usually self-setting. And during this self-setting, they give a lot of heat. They give out a lot of heat. Usually the self-setting process is exothermic. That's why that amount of heat is detrimental. It's not detrimental for cells. They can lower the cell viability. And also for proteins, they can be denatured. Other examples of polymers, other examples of 3D printed materials are different polymers like Güllü hocam, like PLA, or other examples like Özay hocam had given, like polyether ether ketone. These different types of polymers are used for 3D printing, but in most of the time, in most of the time, to keep these polymers intact or stable as the given shape, we use chemical cross-linking. And most of the time, these chemical cross-linkers are toxic. They are toxic to the cells, and also they can denature different biological materials. So this approach is not also applicable for bioprinting. Metals and ceramics, Özay hocam had given a lot of examples in dentistry for the use of metals and ceramics. But again, for different approaches of 3D printing, there is either thermal, a lot of heat to melt the metals, or laser sintering to sinter the ceramic particles. So the amount of heat that is required to keep these metals and ceramics intact will kill cells and cellular features. Therefore, again, use of metals and ceramics is not an option for bioprinting. There are calcium phosphate or bioglass polymer composites that is particularly applied in bone tissue engineering or dental tissue engineering. Again, they give a lot of good results in terms of tissue compatibility. But again, for these composites, usually thermal or chemical cross-linking is used, which again is not applicable from the same reasons for bioprinting. So the final, actually, and only used today option remains to be composites of hydrogels, where we mean hydrogels being highly cross-linked, but polymers with high water holding capacity. Because hydrogels are very porous with a lot of water holding capacity, hydrogels can carry live cells during printing. So therefore, But again, still to keep hydrogels intact, we need to use some type of cross-linking. And because we need to avoid from chemical cross-linking, usually calcium cross-linking, in the example of alginate, for example, or some different types of light cross-linking methods are used to be applied for bioprinting. So when we look for biomaterials for 3D bioprinting, again, we have hydrogels with different stabilizer blends, and hydrogels and possibly ceramics, or sometimes even we read about, for example, magnetic nanoparticles, so different composites of hydrogels with either calcium cross-linking, temperature cross-linking. Again, but when we talk about temperature, we're talking about around 37 degrees of temperature. Because as you know, again, if we reach even up to 40 degrees Celsius of temperatures, that would we would lose cell viability. So we're talking about minor changes in temperature, minor changes from room temperature, and some mild cross-linkers, like some biological origin cross-linkers, are also under investigation. So that's why I'm trying to emphasize or point out that we have a very much lower choice of materials when we try to print cells and biological materials with our bioinks. Now, as a summary, I should say, when we increase the polymer concentration, of course, we get better fabrication, easier fabrication, harder materials, harder constructs, harder stiffness. So that coincides with shape fidelity, but we use cell viability as we increase the shape fidelity. That's why it's a very thin line of optimization of the bioink design, whereas you have easier fabrication, you have shape fidelity, good stability, plus higher cell viability. That's why we need to be somewhere here. We need to look for new strategies that would keep you with lower polymer concentration, so that there is more porosity, there is more exchange of oxygen and nutrients for the cells, but still have good shape fidelity. So when we look at the 3D bioprintable materials, we are concentrating on different hydrogels that are environmentally responsive. There we mean like responsive to pH, responsive to ionic strength, temperature, light, electric or magnetic field. Those hydrogels, those stimuli responsive hydrogels, where of course we define as 4D printing, also suitable for bioprinting. So you can print at some condition, but then increase the stiffness, increase the hardness, and therefore the shape fidelity by some external effect. And usually not only hydrogels, but composites of hydrogels, because most of the hydrogels that we use today do not have shape memory effects, the properties. They are not most of the time stimuli responsive, but we use different additives to make composites of these hydrogels to achieve that environmentally responsive effect. So when we look at common materials that are used, again, ionic cross-linking, particularly calcium-based cross-linking, is commonly applied in bioprinting. But we all know calcium, all of the cells, or cells use calcium, but excess calcium also can lower cell viability, and viability is not everything. Also, we need to be able to keep the cell properties. So therefore, some calcium, excess calcium might change, although even not kill the cells or lower cell viability, but they might change the cellular properties. Particularly, they might cause the cells to differentiate into different phenotypes. So that also has to be, we need to pay attention to how much calcium we can use to cross-link these materials. Photochemical cross-linking and sacrificial scaffolds, also printing using a sacrificial scaffold, printing inside that scaffold and then getting rid of the supporting material is a very commonly applied technique. We do use a lot of blending and addition of nanoparticles, spheroids, even cellular spheroids now are being experimentally tried to increase the printability and stability of the 3D bioprinted structures. There are different types of hydrogels that are used, like alginate, collagen, gelatin, agarose, chitosan, cellulose, hyaluronic acid, and the list goes on. There are so many different hydrogels that are under investigation because they are so neutral most of the time with cellular activity. These natural hydrogels are good candidates for bioprinting, but also some other synthetic or semi-synthetic hydrogels that are tried for bioprinting. But also I want to emphasize here the novel design peptides are becoming very strongly into the field, because peptides we can impose special properties that we want. Particularly design the peptides so that they can be responsive to environmental stimuli. Also, to improve biocompatibility, it means first we need to improve the cell adhesion and also the matrix remodeling properties. After reaching these initial levels, then we also need in bioprinting gels that these hydrogels must be amenable to biochemical modifications, because we need to induce, for tissue engineering applications, we need to induce so many different properties to direct cellular activity. So therefore, these hydrogels need to have active groups on their surfaces so that they can be functionalized further in order to be used in tissue engineering. And last step would be, of course, starting to be able to do large volume printability, which is so far is a secondary need right now. We are still struggling in the other problems that we have in bioprinting. So a very common technique that is applied also in our laboratory too is combination of different materials. Because of all those requirements, keeping cell viability plus the structural integrity is not very easy to accomplish with a single material. Usually hydrogels are good in keeping cells viable, but mechanically they are not strong. Therefore, using different materials, for example, in this example, there is the calcium phosphate in some layers that is keeping the integrity, structural integrity of the material, but other layers being printed by hydrogels that are keeping the cells alive. Also, another commonly used technique, commonly not, I shouldn't say commonly used, but recently experimentally tried quite often, is a core shell printing in a core shell fashion. So in this case, again, two different nozzles printing two different materials, but not in different layers, but in a core shell fashion. So one layer would be responsible for cellular viability, whereas the other layer would be responsible for structural integrity. So when we look at cell survival during printing, or when we're designing our bioinks for bioprinting, we need to pay attention to oxygen. There should be enough oxygen during printing and after printing. Also nutrients. The cells, all the time, the cells should be able to get enough oxygen and enough nutrients. Temperature should be kept in a cellularly acceptable level during printing again and after printing. So also the shear stress. Usually this factor is commonly overseen, but no matter what type of printer we're using, during the injection, or even in the inkjet or laser printers, during the printing process, the ink is subject to quite a lot of shear stress. And this shear stress can affect cellular viability tremendously. So keeping the chamber temperature high or using a lot of shear during printing, you can get a stable structure, but you might possibly lose most of your cells during printing. So therefore, particularly some simulations or in silico representations of the printing process would be very helpful, because in the literature it is known how much shear can different cell types can bear. And even some shear is helpful for cells. It does trigger some types of differentiation, or it might even increase cellular viability. But above a threshold level, shear stress definitely would lower your cellular viability, would change your cellular characteristics, and in the end, it might even cause your cells to die. So it is very much advised that you do in silico modeling of your bioprinting process, in which case the parameters, your dispensing pressure, how much pressure you're using to extrude the cells through your nozzle, your printing speed, your chamber size and chamber shape, the geometry, the nozzle geometry, the diameter, the nozzle shape, again, how steep or how leveled your nozzle is. These will all change the amount of shear stress that's applied on your cells, and the pressure distribution will also change. So therefore, I do recommend you definitely include an in silico modeling of your bioprinting with the properties of your own cells and with the properties of your own bioink, so that to optimize these printing parameters to keep highest cellular viability. And also to increase cell survival after printing process, there are different techniques, there are different approaches to induce pre-vascularization or rapid vascularization after bioprinting process. Again, this includes use of different techniques. For example, using a 3D printed structurally stable bone scaffold, and in that scaffold printing of cell-laden hydrogels. So again, one material keeps the structural integrity while the other material keeps the cellular body alive and healthy, and in between using vascular grafts, so that after, particularly in tissue engineering applications, after implantation, it can keep the cells still viable. So we do have a lot of different approaches that to improve cell viability, but choosing the right bioink, that is not easy, that's not trivial. You need, most of the time, a lot of my students, for example, think that the first time they try in the laboratory, they will succeed. No, that's not the case. It needs quite a lot of time and effort to optimize bioink concentration. Optimization of not only the ink, but the printing time, minimizing the shear, so printing parameters, control of temperature, control of vascularization afterwards. In proper microscopic characterization, again, the thickness or pore structure. And possibly it would be very late applications, very recent applications include different types of sensors during printing and after printing. It's very advantageous to employ online monitoring of relevant physical and chemical values like the oxygen concentration, also the shear stress or nutrient concentration. All of these, if it is possible to online monitor these parameters during printing, that would help a lot to keep the cell viability in a maximum. And still unsolved problem, bioprinting of macroscopic meaning that printing of tissues and organs. I know we will get there in a few years' time, but still we have great success in thin tissues, but as the scaffold size gets bigger, these become more problems. So macroscopic, viable, and mechanically stable constructs. But I hope with these little bits of clues, I might have had an idea, given you an idea on how to continue. So good luck. We are continuing working on this, and hopefully more and more people will join the bioprinting community too. So thank you very much, and I would be happy to answer any questions.
Yes, please. Any question?
I think not.
Yes. Eileen Hocam, I have a question.
Please.
Because bioprinting is a very interesting topic, especially for the regenerative medicine, artificial organ design. As you emphasize, nowadays it's possible to design thin tissues, but for complete organ regeneration, there are a lot of problems to solve. Now, what type of materials, for example, natural biopolymers are my favorites, of course.
Yes, yes, mine too.
You know that biocompatibility properties are very high for them. And What other biocompatibility properties are important during the design of the bioink? Not only for the natural biopolymers, of course. If we talk about bioink for tissue design, how we're going to biomimic them is a big problem. So what type of biocompatibility properties are important in the design of these type of bioinks?
Thank you, Hocam. Of course, biocompatibility, yes, but plus biocompatibility, we need to be able to functionalize these hydrogels. Because for tissue engineering, usually when we look at our own tissues, no tissue is composed of a single cell type. There are different cell types in all of our organs. So one hydrogel, biological hydrogel, can be good for one cell type, but another, if we try to put that in a tissue concept, it might not support, it might not have good biocompatibility with other types of cells in the tissue. So to be able to impose that compatibility with different cells, we need to be able to add some other functional groups. So good for bone tissue engineering, for example, it might be good for bone, but then what about the cartilage next to the bone? Or what about the periosteum around the bone? So it is very important that we can put different elements to make it compatible with surrounding tissues also. And like I try to emphasize, vascularization is a very, very big problem of all applications of tissue engineering. So to be able to have vasculature-like structures within the bulk is important. So either we put the veins there, or it should be after the fact, after printing, it should be easy to create new blood vessels inside. That's why hydrogels are important, so they have space in it, space for the invading vessels to get in and complete the vascularization.
Yes,
so
you're
depending on the application, what tissue you are focusing on, we need to be able to make composites of or blends of biological hydrogels. So I don't think there will be a single material that will answer all the questions. I think we need to go with different composites.
I completely agree with you. That means in the design, inverse design technique is important. Depending on your problem, you have to design different bioinks for specific purposes. Thank you, Hocam. Thank you for your valuable knowledges, and thank you that you accept my invitation and join to this symposium and share your experiences with us. Thank you.
Thank you very much. Bye-bye.
Now, the last presentation topic is 4D printed smart dynamic materials in biomedical applications, chemistry, challenges, and future perspectives of that. I'm going to present this last topic. Of course, up to now, all of the researcher professors share their experiences with us, and now at the end we're going to discuss a material base 4D printing and 3D printing also. 4D printing of smart metamaterials, applications of them in tissue and organ regeneration, developing artificial articular cartilage tissue, and one of the most important biocompatibility property, which is a hemocompatibility of these smart materials and future perspectives of them. Before starting to discuss, the problem is very important. What is a problem? Problem is lack of number of donors for transplantation. And according to the National Health Service of United Kingdom, the total number of patients registered for a transplant has decreased slightly by 2%, so that 4,256 patients waiting for transplants at the end of March 2021. Only 5,307 temporarily suspended from transplant list. So these are very important statistical results that help us to focus our attention on how to design, how to biomimic artificial tissue and organs with the help of engineering technologies. Now, current UK statistics for organ donation and transplants are shown here. 6,401 people are waiting for a transplant. Only 938 people have received a transplant. So additive manufacturing technology plays a very important role in biomedical applications to be able to solve these type of problems. The important challenges are listed here. Limited choice of materials is very important. Poor mechanical properties of the designed biomaterials and hybrid systems is very important. Low dimensional accuracy, customization of fit and design, high cost of printers and speed of bioprinters are very important problems to solve in this discipline. So what we have to know, we have to design bioprinted artificial tissue organs and biomedical devices and try to improve their mass production. Tissue engineering and regenerative medicine produces procedures, of course, fill the gap between number of transplants awaiting patients and donors available. So 4D biomanufacturing is an emerging technology. Most of the presenter present 3D plus 4D biomanufacturing. And now we're going to check how it is a technology that we can improve for biomimicking tissue and organs. Criteria for 4D bioprinting in tissue and organ regeneration is very important, and now we're going to discuss smart metamaterials, applications of 4D bioprinting in this field, developing artificial articular cartilage tissue, hemocompatibility of layer by layer films, which is a very important biocompatibility parameter of the implantable devices, and also tissue and organs and drug delivery systems and their future perspectives. Now, 4D printing, we said. As Hocam said, the difference between the 3D printing and 4D printing is one extra dimension which is related with the time. So in biomedical applications, it provides improvement, and you can be able to configure any smart material in response to the stimulation of the post-printing process. So this is very important for us in the design. This figure is a very simple diagram of the 4D printing. As you see, temperature, pH, humidity, electric field, magnetic field, light, acoustic wave, multiple stimulus combinations are all fourth dimension of the 4D bioprinting. But the most important point here is this bio-ink, which is either a hybrid system and smart material system. They are very, you have to design them as an intelligent systems. So now these bio-inks, either they might have cells, growth factors, other biological molecules within them, or after the 3D technology, after these scaffolds prepared, you may be culture the cell on them. So there are two ways of cell culturing in tissue engineering by using 4D bioprinting technology. Applications are very important, of course. Tissue engineering, biosensors, bioactuators, and biorobotics are important applications. If we check the effects of 4D printing for manufacturing, of course, in this presentation, we're going to focus on the materials, flexibility, shapes, and shape memory-based programming of them. What is a process flow for 4D additive manufacturing technology? The process flow can be categorized under three headings: smart materials, static structure, and dynamic intelligent structures. Smart materials can be grouped under multi-material 3D printer and inverse problem modeling, as Associate Professor Gül Hocam discussed with us. And the static structure, stimulus mechanism, interaction mechanisms, with either by physical, biological, mechanical, and chemical stimuli parameters. Dynamic intelligence structures are also categorized under two headings: final smart product and complex shapes can be produced with the dynamic intelligent structures. Now, biomedical applications require tissue regeneration, drug delivery system, and diagnostics. For tissue regeneration, for example, artificial skin regeneration, bone regeneration, cartilage, articular cartilage regeneration. All these topics are very important biomedical applications for the personalized medicine and regenerative medicine. So drug delivery systems, targetable drug delivery systems, controls, sustained drug delivery systems, all these uses either micro or nanotechnology, and with the help of them, you can be able to add these drug delivery systems within the bioink and provide multifunctional end product for biomedical applications. Diagnostic also the same. Now, theranostic nanoparticles are very good example for them. And after the design of theranostic nanoparticle, these particles have both diagnostic and therapeutic properties. You can add them into the smart hydrogel and with the help of the biomanufacturing, you can be able to create systems that can be targeted and help to diagnose and apply the therapy at the targeted place. So these are very important designs in biomedical field. There's a great demand for smart responsive materials. They have to be sensitive to external triggers such as biological signals, pathological abnormalities for the development of next generation precision medicine. Now, examples are given for the biomedical applications, cell scaffolds. What type of biomaterials are used for the cell scaffolds, and what type of printing methods, either 3 or 4D printing methods. As Özay Hocam explained and summarized them perfectly, stereolithography, fused deposition model, direct ink writing, depending on the type of the biomaterial and the end product that you aim to design, different printing methods should be applied. A vascular stent is another important biomedical application. Medical equipment such as implantable bioinks, implantable biosensors, real-time monitoring systems, all are also can be designed by using bioprinting technologies. Polyurethane, diacrylate, semicrystalline polymer, methacrylates are types of polymers that are used in the design of medical equipment for vascular stent. For example, shape memory polymer systems are used, polyurethane, diacrylate, and different types of either natural or synthetic polymers are used. Now, if we continue on the applications, tracheal stent, occlusion device, and bone scaffolds, all these are types of biomedical applications that different either 3D or 4D printing methods are applied. And as you see, polycaprolactone, methacrylated polycaprolactone are two important polymers that are used in the design of the tracheal stent. Now, the problem is how we're going to analyze, characterize stimulus and responsive materials. This is very important. And these are next generation targeted therapy. And in the biomanufacturing of artificial organs and tissues, we need biomimicking of these smart responsive materials for specific problem. For example, if you are going to focus on X tissue, you have to biomimic that tissue, and during the biomimicking, different types of biomaterials should be used. And of course, the microenvironment around that X tissue is also very important. The stimuli, either climatic stimuli, biological signals, or everything are under your responsibility. They should be responsive to these changes. These are very critical in biomedical field. That's why it's an interdisciplinary research. Tissue repair, medication administration, diagnostic are important problems to solve. Now, how many types of stimuli are there? Of course, we can roughly categorize them under three headings: chemical, physical, and biochemical stimuli. Uh, Factors are also listed here. For chemical stimuli, pH is very important. I will show you what we have done in our research. For example, stimulated tear fluid has pH blah blah. So that's why we have to design a synthetic one and try to understand how the designed hybrid system reply to that pH value. Of course, for different pH values, carbon dioxide, carbon monoxide, redox chemical solvents. What are effects of the chemical stimuli? Transform molecular interaction is the most important effect. Physical stimuli also has factors such as temperature. As temperature increases, what happened to the designed smart material? Light on the electromagnetic spectrum, different wavelength ranges, UV visible, infrared, X-ray, so gamma rays, for different types of light wavelength ranges. What are the stimuli of the hybrid system? That is also very important. Electrical field, under the electrical field. So when you apply an electrical field, is that trigger the shape either to expand or construct? Mechanical power, ultrasound. Under the ultrasound, what happened? So polymer chains dynamics can be altered with the physical stimuli. For example, theranostic nanoparticles, with the help of the ultrasound waves, they can be burst at the targeted region. So these type of designs are very important. Biochemical stimuli, such as enzyme, glucose, antigen, amino acid, nucleic acid, and polysaccharide. Effects of these biochemical stimuli factors are listed here. They might cause biodegradation, competitive binding, mediated material. As everybody knows, polymers are catalyzers, and they have a lot of cycles in the biochemical reactions. Now, if I try to open chemical stimuli, why we are trying to explain them in details, and in the design of the smart material, why they are important for us in the biomedical application. We know that variations in physiological conditions such as change in pH, ionic concentration, are often clinical hallmarks. And cancer, neurodegenerative disease, infections, cardiovascular disease, rendering them important targets of consideration when designing bioresponsive materials. For physical stimuli, I only try to give one example for that. to emphasize the importance of the physical stimuli. For example, the application is minimally invasive surgical approach, and in this design, the designer tried to use thermoresponsive polymeric materials because of the glass transition temperature. The only the shape memory effect works only on materials with glass transition temperature lower or equal to body temperature. So that's why for minimally invasive surgical approaches, the parts that are usually preformed at temperature about glass transition temperature, printed parts become smaller and more compact. And after they implanted, cooled to temperature below glass transition temperature, and they maintain small and compact shape during the surgery. So this is very important application for taking care of the physical stimuli. These type of thermoresponsive polymeric materials are smart, intelligent materials. So biochemical stimuli, of course, enzyme stimulation. As we know, enzymatic degradability, supramolecular architecture change, swelling, collapse of structure, transformation of surface properties, all these are very important in the field of tissue regeneration. Implants made of these materials are able to either to biodegrade and remove naturally from the body after they have fulfilled their function. So enzymatic degradability property is one of the important property in tissue engineering applications. Now, in the advanced materials strategies for additive manufacturing, smart materials that we can be group them as shape-shifting material, piezoelectric materials. These piezoelectric materials can produce electric energy upon application of mechanical stress, and quartz and zinc oxide are two examples of them. Biomaterials such as hydrogel, biomaterials, collagen, alginate, silk fibroin, chitosan, these are important biopolymers that we are using in our research. Conductive materials, liquid metals, and carbons are important. Now, in this presentation, we are going to focus on the hydrogels. These are types of them, poly and isopropyl acrylamide, that have both temperature and ultrasound, polyvinyl alcohol as ultrasound stimuli. They cause physical and chemical changes such as structure deformation, and in the biomedical field, they have a lot of applications such as biosensors, drug delivery systems, ophthalmic applications, and etc. in tissue engineering. Chitosan is another important natural polymer. It is responsive both for the ion concentration and pH. Physical phase change has been occurred, and cardiovascular graft round dressing are also potential applications of chitosan. Of course, you can modify chitosan either by cross-linking with another polymer, either natural or synthetic polymer, or grafting another polymer on it. You can be able to modify and use the modified form of it. Polyethylene glycol is another important hydrogel that has self-folding physical changes, and structural switches and stamps are important applications of it. Now, I want to talk about one of the research that we have done and published in International Journal of Biological Molecules. This is for smart biomaterials, and we try to biomimic human articular cartilage. Yeah, of course, as we know, biopolymers are the greatest option of synthetic petroleum polymers with considerably renewable, biodegradable, and environmentally uh, sound characteristics, but they are not supported by mechanical properties. So, in order to improve the mechanical property of the biopolymer in this design, we try to find out material that can be able to biomimic the extracellular matrix of the articular cartilage, and also has a high biocompatibility, improve the mechanical strength of the hydrogel. So this is the first step of designing bioink. Uh, Therefore, uh, in this study, we try to use biopolymers such as chitosan is the one, sick fibroin is the other one, and eggshell membrane is used to be able to mimic extracellular matrix. The end product hydrogels, they have interconnected structures, and we can be able to synthesize them by ionic gelation method. The SEM micrograph of the hydrogel, please don't forget that we aim to use this end product, this hydrogel, in the biomanufacturing, either in 3D or 4D bioprinting technology. So before using them, we have to characterize and try to understand the biocompatibility of it. And of course, physical, chemical, and biological stimuli are also tested here. Morphological, physiochemical characteristics were determined by scanning electron microscope, and these hydrogels show superior mechanical properties for desired application and support growth, adhesion, and differentiation of human chondrocyte cells, where high viability was observed. Now, these are results of our work. Entity cell proliferation assay has been done, and high viability of the human articular cartilage cells in this hydrogel was observed, and we hypothesize and propose these hydrogels in the design of the human articular, of course, artificial human articular cartilage. Now, at the end, the novel hydrogel, which is chitosan secretoin eggshell membrane hydrogel, is a stimuli responsive hydrogel that can be a good candidate for designing human articular cartilage scaffold by using 4D biomanufacturing because of the chemical stimuli towards pH, ionic concentration, and biodegradability property. Biological stimuli, we have done cytocompatibility, cell culturing, and biomimicking of articular cartilage extracellular matrix. And physical stimuli is temperature that we check. So this is one of the work that can be proposed to be used as an implant design for articular cartilage by using 4D biomanufacturing technology. Now the second one is related with the polyelectrolyte complexes. Here also we use bio-based polymers, and hemocompatibility, as we said, during implantation there is a contact with the blood, so hemocompatibility is one of the important biocompatibility property before designing the end product. The hydrogel or these type of layer by layer hydrogels should be able to blood compatible with the contact of the human blood. And of course we try to improve implantability property of these smart materials, stimuli responsive smart materials. So what we have done, we purified silk fibrin from the bomboximori, silk cocoons, chitosan sodium alginate also dissolved and used. Of course, in order to improve the hemocompatibility property, clopidogrel bisulfate is embedded within the structure, and we use 3D extrusion-based printing technology for the three layered by layered structure of these polyelectrolyte complexes. So chemical stimuli have been done for pH and biodegradation. Of course, after characterization, Fourier transform, infrared spectroscopy, scanning, electron microscopy, differential scanning, calorimeter, and atomic force microscopy have been used in the characterization. Swelling kinetics also work, and at different pH we check behavior of the composites. Now, biochemical stimuli polyelectrolyte complexes have been done in vitro hemocompatibility works, and in vitro anticoagulation, total cholesterol, complete blood contact, in vitro platelet attrition, erythrocyte morphology analysis, all these have been done for the different design of our polyelectrolyte complexes. They are either 3-layered by layered or 2-layered by layered structures. Now, in vitro anticoagulation, of course, clotting time, APTT time, INR, all these have been checked, and we reported them. They are all within the range. And blood cholesterol albumin analysis, these are also are results that are expected within the ranges, and complete blood count. At the end, we've recognized that our layer by layer polyelectrolyte complexes these complexes have no effect on the clotting and cholesterol level, albumin level, and other parameters of the blood. So all these are helpful for us to improve our morality and work on platelet adhesion and erythrocyte morphology. As you see, we haven't observed any adhesion of the platelet, and nothing has been happened to the erythrocyte. These are scanning electron microscopy, micrographs, and atomic force microscopy that we have done. So at the end, results show that characterization support PEC1 design to be the most superior material and favorable surface topology it has, and it has least surface roughness. For the non-thrombogenicity and favorable for the swelling kinetics, same material is favorable for swelling kinetics. And if the outer layer is chitosan, then we observe that this does not induce swift activation of the coagulation cascade. So these are works that we try to modify smart materials, hybrid systems for bioink applications, and for specific ones, such as the first example that I show you is related with the artificial cartilage, human articular cartilage system. So, recent challenges and future directions of the healthcare enabled by the additive manufacturing. Resolution of the bioprinted tissues is the main challenge, and the key feature for bioprinting of organoids. Of course, tissue engineering, regenerative medicine, development of this area of more printable smart materials for scaffolds, implants are very important. Uh, and of course, biomimicking of the product is very important during the design. For this purpose, the research direction of the biomanufacturing has changed towards the fabrication of smart materials. And in addition, structural design, printing techniques, ink materials, extremely crucial for achieving a 4D effect. And specific to tissue and organ regeneration application, the printing materials must be biocompatible and capable of performing dynamic 4D processes in a physiological environment. And now I thank you all for your patience. And if you have any questions, please do not hesitate to ask me. Is there any question? Good. Now, it's time to finalize our second 4D Additive Manufacturing Regenerative Medicine Symposium 2022, organized by Near East University Center of Excellence, Tissue Engineering and Biomaterials Research Center. I would like to thank our partners, Sabancı University Sunum Nanotechnology Research and Application Center, Near East University Narita, Near East University Dasam Institute, for their valuable support and participation, especially for the Professor Dr. Ali Koshar, our distinguished professor, and Associate Professor Dr. Güllü Kızıltaş Şendur. Now, I would like to thank Ege University Department of Bioengineering also for their valuable contribution for our symposium, and especially for Associate Professor Eileen Schandemer for her effort on this field. The biodesigning team working perfectly in Ege University in this field. Now, let me also thank to all the participants of the symposium and colleagues of us, and I wish all of you a fruitful and enjoyable academic life. Thank you.
Eğer ki hayatımızda hiç eğer olmasaydı nasıl olurdu? Size şöyle söyleyeyim. Her şey daha az parlak, daha az yeşil olurdu ve daha az parlak yeşil. Çünkü eğerler ormanların derinliklerinde tek bir kibritle derinlerin kıvılcımını ateşler. Eğerler Nobel ve Guggenheim'ın aklına takılır ve o kodu bu kodu çözerler. Eğerlerle içinizden haykırmak gelir. Eğerler bariyerleri kırarlar. Asla yalnız yürümezler ve aşırı bulaşıcıdırlar. Eğerler aşikardır ve son anda golü atarlar. Eğerler dünü umursamazlar, robotlarla bile konuşabilirler. Karşı takım soluklanırken oynamaya durmadan devam ederler. Sadece basit bir kelime öyle mi? Hayır. Eğerler asla uyumazlar, hep daha fazla çaba gösterirler. Eğerler bakar, araştırır ve en beklenmedik zamanda ortaya çıkarlar. Eğerler klonlanarak çoğalırlar. Acaba gerçekten yapabilir misin? Yaptın bile. Eğerler aklınıza girmeye çalışan güler yüzlü şakacılardır. Eğerler kapıları açarlar, asla kaybetmeyeceklerini bilirler. Ve biraz gün ışığına her zaman hazırdırlar. Her şey bir eğerle başlar. Çünkü eğerler ne zaman dönüşür, ne zamanlarsa şimdi. Ve şimdi nasıla dönüşür. Nasılsa asıla. Eğerler bakış açınızı değiştirir. Eğerler oyunu değiştirir. Eğerler dünyayı değiştirir. Biliyoruz. Çünkü biz eğerlerle çalışıyoruz. Yakın